Yes, I'm here. We should get started.
Okay.
So we start?
Yeah, it's all yours.
Okay, thank you. So I will talk now about multi-stage program when we have many stages. And we need, in order to do something positive, we need some structure. Because the original thing that we have here almost hopeless. If I don't assume anything about this process, I need to look at this functional, and it will quickly become unmanageable at all. There's no simple concept of the state here, for example. What does it mean? Also, some people say that. Okay, so one of the classical approach, everybody knows about that, using dynamical programming. And this is where the progress is. I try to explain the scenario approach which work reasonably okay with random generation for two-stage does not work in multi-stage, or at least it's not clear. Because the computational complexity grows also exponentially with number of stages. So now, if I want to use dynamical programming, which has some specific form here, there's some different questions. Okay, so let me, I think now that everybody knows what dynamical programming is, because this is one of the main tools of all that. So let me remind you that this is denote this the history of the process. One also can write it in terms of filtration, but it's more intuitive, right? And we can write dynamical equations. And this is a way how we can write them in very general way. Very general. It's not very useful, but conceptually it is like that. What we do here, right, when I talk the expected value, we decompose the problem into stages, into this what is called value function or cost to go functions. And you see this, the whole process here of decision is conditional. We observe this realization of the data and we make the decision, right? Because of that we decompose that, taken this conditional expectation. At the first stage, eventually at the first stage, one has to solve that problem, where this is a corresponding value function. If it is two-stage, we have just one, right? This is what I formulate here. Now, is it really any useful to write these dynamical equations like that? These dynamical equations, as you all know now, will know now, summarize what you look at a particular point and look value what happened in the future on conditional value. At this form, it's not useful at all, because if there's several how one can use that, how to compute this expectation, one need discretization, I will talk about that. But one of the main questions here, how can I put in a computer this function? How, because when I go backward in time, as everybody is doing, right, that I have to keep my function values of that. Only in very simple cases it's possible to write analytically. So if I want to do it like that, I have to remember this, it's function of many, many variables. How you can represent function of many variables in a computer? It's not trivial at all. In fact, it's impossible if this number of these variables is very large. So the basic assumption that we make now, right, this it has different name, that the process is independent from one, stochastically, from one stage to another. Let's call it stage-wise independent. It doesn't need to be IID, but at least it's independent. This is probably the simplest if I want to model that. This is a sequence of random vector. This is probably the simplest way to do that if I want to model. In that case, I only need to know marginal distributions of every vector. I don't need to remember the past. And indeed, it's not difficult to prove in that case, all right? That the so-called value functions here, this right expression, they don't depend on the past observations. When you look with control, when you look at control and also to less MDPs, this is a very essential thing about that. When they consider the noise, they consider this as a noise or disturbances. So the condition is independence is very natural. Here it's not. So, but let's for a moment assume that. Now, then my value of this cost to go functions only depend on that. It's possible to do more precise and possible to introduce also concept of state variables. This is what I have to remember every time they make the decision. And the solution is that. So if somehow I can compute these functions and I can keep it in the computer memory, in a sense I solve the problem, because my optimal solution will be given by this sequence. I can go forward, generate my data, these observations, and every time, suppose if I can solve that, I solve the problem. Now, still, there are several questions. One obvious question is, as I said, it's not natural in any way because there's a Markovian type of structure. I don't have much time to talk about that. Sometimes it's possible to do something, but suppose for a moment it's correct. Yet, okay, I have this decision variable. This is what you can think about this is state. It's also possible to separate what is called sometimes state variables. It's what is local. This is what I have to remember if I go from one stage to another. Okay? Can I solve it? So if it has dimension 100 or 1,000, and now it's not uncommon to have this, it's still, I have still this problem. It's a classical problem of curse of dimensionality. And let me say it's very clear. Nobody solved this problem of curse of dimensionality. So surprisingly, in some cases, something possible to do, which is almost a miracle, in my opinion. Okay. Now, this is I listed here of this approach of dynamical programming in this setting that I'm saying here, setting. Okay. Even if we assume stage-wise independence here, suppose we assume it. So remember this. What is the problem? One problem is that I still have to compute the expected value of that. This is the same as in two-stage case. How can I do that? I can do discretization of that by saying sampling Monte Carlo. It's the same thing. Okay? And we have quite good idea how many points we needed for reasonable. I'll show you probably if I'll have time. I'll show you some numerical results how to do that. So we replace that by discretization, usually by Monte Carlo, quasi-Monte Carlo. It's questionable if it's useful or not to do that. Okay? So again, I need only to, because of this assumption, I need to only marginal distribution, but it's still random vector. It may have dimension 100. Okay. Also, at I have to solve the optimization problem. How I solve it is a good question, even in linear case. Why I saw in the beginning, why I wrote linear, even in linear cases, we'll see it's very non-trivial question. Okay. Now, what is extremely important is here, right? As we'll see in linear case, these functions are convex with respect to the decision variables. Right? For example, in linear case or more generally some convex case. For optimization in this area, convexity is extremely important in optimization. More important than the smoothness of differentiability, much more. So how one can use that. This is what I said, okay? This is how one can put it. And for large, let me also say that trying to make discretization of the decision variable of state doesn't it doesn't go anywhere. If it is one dimensional, you probably make discretization of that, and then it becomes finite vector. But a number of discretization points you need to approximate it reasonable way grow exponentially with dimension of xt. So for even for 3, it already doesn't work, this discretization. So one has to do something else. Okay. So again, remember when we talk discretization, one talked about discretization of the process of continuous distributions. But and this we have to do, we'll see that. Right? But also discretization of the decision variables of the state space doesn't happen for only very simple cases. Now, so the strong indication that again, generically, multi-stage computational problems are intractable, even if one wants to solve that with not very high accuracy. Okay? So what can one do realistically? And there are different ways how people try to address it. Now, I'll talk about one particular way. That's just now. There are several ways. In other words, one needs to do some type of approximation. The question, what is a reasonable approximation? Right? Can the error of the approximation can be estimated, and so on and so on. So I will talk about that. It will be important now that the constraints are linear. One can do more general, but it's sufficiently general. Here, you can think about that. The convex function of just even linear functions. Please remember that eventually, what I'm interested in is a first stage solution, typically, because this policy that I have here, typically people recalculate as information is coming in. Okay. Now, can one do anything about that? Okay. Now, what became very popular recently is a cutting plane time method, which has a very long history. Okay. It goes originally to this, you see this how 60 years ago for deterministic problem. This is a very simple algorithm for convex problems that one only need to know how for deterministic convex problems. And it's generate cutting planes at cutting planes. I don't know if you saw that. If you work on optimization, I'm sure you saw that type of things. And this very primitive algorithm, which was improved enormously by all types of methods. At the moment, in deterministic optimization, for cutting plane, probably the best method is level method, due to Nesterov, Nemirovsky, Lemarchal. Or trust region will already make huge improvement about that. So worst case complexity of that is bad. And it's understandable why. Now, this was extended to, this cutting plane method extended to some place to this, in this paper, to multi-stage. And in this paper, it was considered basically finite now. It was in terms of scenarios mainly. It was later extended more. And then it was this was this paper, which became very well known. At the beginning, nobody really paid much attention to that because it was developed by engineers in Brazil. Then was some paper, but then it became very, very popular because sometimes it can solve the problem with reasonable accuracy. Okay, so how it works, I don't have much time to talk all the details, but basically the basic idea is rather simple. Okay, remember this, we have this, this dynamical equations here. Okay, and these are convex functions. It's certainly true if this objectives are this convex with respect to xt, and say we have linear constraints. So we approximate it by piecewise linear function, cutting planes. We approximate it. How one approximate it? one can look at as a particular case of approximate dynamical programming by adding more and more cuts. Right? One choose some points at every stage. These are usually called trial points, going backward in time. And every time at the trial point, this is your current approximation of your, which will give you lower value. It's below, it's cutting plane or supporting plane type of things, right? And one choose some additional point going backward time and add to that cutting plane, solve this computing subgradient of that. For that one, it's not difficult to show. One needs to solve the dual problem. And it's a linear problem. Why it's linear? This every time one solves linear problem. Why it's linear? Because this is given by maximum of linear or affine functions. These are linear constraints, so it's possible to write as a linear programming problem. So one going backward in time, adding more and more cuts, and then one choose new trial points and going this in circles. How to choose the trial points every time? It's a good question. One possible question is that one possible approach is the following. First of all, let's see that this is so-called true cost to go functions, right? This is low approximation by construction. And this is piecewise linear function, the maximum of affine functions. Okay? Now, every time we constructed these functions, somehow, right, we generated a policy. We generate a policy for true distribution or for discretized distribution. How it works? We simply go backward in time, right? And every time we solve this problem. Okay. For replacing this, we replace the true cost to go function by its approximation. So we define the policy, and we assuming it's possible to solve, because every time it's linear. Right? If it is not too large, it's possible to solve it. It's you can think about that. You're going forward in time, generated this randomly generated this sequence of random vectors and solve every time, and it gives you solution. And this people usually use as a trial point going backward in time. So and it gives you low bound, because this is give the low bound. Eventually, if you solve this going backward in time, you compute the value. This is value, right? Approximation of that. And it gives you upper bound, because every time one randomly generates the sample path or scenario, it gives you a point estimate of the value of your policy. And this can be averaged, and let's give you stochastic bounds. So one has lower bound, upper bound, stochastic, and now we can see the gap between them and give you certain stochastic guarantee how one solve the problem after discretization. Even more than that, it can be applied also to what we call to the true problem, because this also you can apply the same policy to the true problem. Simply one generate random sample from the true distribution, not from discretized distribution, give you upper bound, and it's stochastically, because of that, give you lower bound. So one can estimate the error of your solution. Amazingly, sometimes it works. And what I mean it works, for huge problems, which are absolutely inaccessible from scenario point of view. The number of scenarios there is much larger number of atoms in our universe. One can solve the problem with proof accuracy, say 4%. You say it's bad, or 10%. And it's guaranteed. Usually the quality is much better than that, but it's almost a miracle that one can solve problems like that. Now, why it's not obvious? This is what I say. Okay, this one can consider low and upper bound. Now, this is a question. This became very popular method, especially in power generation type. And this can be extended to also mixed integer problem. Also, it's much more difficult to solve than linear case. Sometimes it's solved. There are many questions about that which are really not well understood. In other words, why it sometimes works. Because from a generic point of view, right, if I have convex function and I need to approximate it uniformly, well, because my solution is random. I don't know where it will hit next time for different sample paths. Number of this, generically, number of the piecewise cutting planes that I need also grow exponentially with dimension. So why sometimes it solves even the problems where the state space has dimension 20. You say 20 is not much, but still, sometimes people claim that they solve with dimension 100 or 1000, which I have doubts, but this probably depends on the structure of the problem. So probably the possible answer to that, and it's not obvious, right, that we don't need to approximate this value function uniformly everywhere. So the solutions that really matter and what happens, they all probably either low dimension or they only in certain areas. We don't need to approximate the value functions, cost-to-go function, uniformly everywhere. It's not possible, or it's not clear. And this method, when we do this randomization, when we go randomly generate, will probably tell us where it's important to approximate. And it depends on a particular problem. Generic answer is no, not much you can do. But it's amazing that some cases we solve it. I'll show you examples. Why? It's a very big question. Now, I listed here some of the basic questions to this algorithm, which became very popular. And in fact, this is probably the only one at the moment that we have for that type of solutions. For that, there is, even to prove convergent, it turns out to be technically non-trivial. Also, it's quite clear why. But what is a convergence rate? From empirical observation, it seems that the complexity of that grown maybe not exactly linear, but more or less not much with number of stages, but it obviously grow badly with dimension of the state. There's some papers recently were published that they try to address that. We shall see. So when does it work? Again, nobody solved this problem. Nobody. Don't tell me that somebody solved that. But sometimes it works. Why? Can one just define this problem when it works? From empirical observations, from experience, it works sometimes. From an optimization point of view, this algorithm is a primitive cutting plane algorithm, basically. In two stages, it's exactly a algorithm. The problem with that as one add more and more cuts, it's become the solving linear problem become more and more time consuming, and it explodes. So can one do anything better than this primitive type of algorithm? So far, there is no evidence of that. And the reason for that is that in deterministic case, why it works? Because in deterministic case, one needs to have good, accurate approximation near the optimal. In the beginning, you don't need to have, when you're far from the optimal, in the beginning, one doesn't need to have very good approximation of the function. You have quick progress. As you go closer, you need to more and more accurate approximation. Here, we don't have it because the solution is itself is random. So one can talk about first stage solution deterministic, but it's absolutely unclear how more advanced, much better algorithms can be applied. It's also this, maybe I also say that in two-stage, in static case, the stochastic residual, stochastic approximation type of approach worked very well in some cases. It's absolutely unclear how to do it here. for say more than 3 stages. There were recent papers by this Berlin that they pushed, I think, to 3 stages or even 4, but for 10 stage, one can forget about it. It's absolutely unclear how to make it because one has to reconstruct the whole policy.
Alex?
Yes.
So could you give us some intuition about what do the do variables mean? And also like how can we interpret the cutting planes?
You have this, you see, this is original, okay? So every time, if I knew this function, right, and somehow I can keep it in the computer, basically I've solved more or less problem if I can solve it. So what we do every time, it's convex function with respect to xt. We approximate it by maximum piecewise linear functions, right? We give low approximation of that. How we do that? Okay, we add more and more cuts to that. Okay, we add more and more cuts at certain points. Every time I want to add, I don't know what the real function is, so I replace it by this approximation. We solve this problem and we compute the gradient, right, of this subgradient of that. If I knew subgradient of that, right, at least one, I can add the corresponding supporting plane.
Mm-hmm. Yeah, so this is the intuition for cutting planes in optimization, right? But in stochastic programming, does it have any particular physical meanings? So I ask these questions because in Markov decision process, the Markov decision process could be written as a linear program. And then there is duality, where primal variables corresponds to Q functions or value functions, but dual variables corresponds to some occupancy measure under a policy. So there's some very interesting duality between a distribution and a value function in MDP. Is there something related in stochastic programming?
Just one moment. I'll give it in a moment. Sorry for this break. Okay. You're absolutely right. And if you look at this original problem, when the number of scenarios is finite, linear, it's a huge, you can think about it, it's a huge linear programming problem. Huge, astronomical. As a linear programming problem has dual. No, it's standard. In just one minute. I'm sorry. Yulia. Okay, Yulia actually didn't make session. I'm very sorry, it was my doctor. Okay, so you're absolutely right. So there's a dual problem. The question how to use it. And I hope I'll have time now to show how you can use dual. Is that your question?
Yes.
This is your question.
Yeah,
because
the question
here,
is to understand what does the dual program mean physically.
Yes, I will try to show you. Yes. Here, the dual problem is just for this one problem for how to compute subgradient. No, this is a classical in linear programming that how you compute the subgradient. For that, you need to solve the dual problem. Okay, I hope I'll have time to do that. Okay. Okay, so notice how this algorithm works. It goes forward and backward, okay? And hopefully it converges. Now, so this is this natural questions about this, which are don't have good answer yet. There's recently some papers, a couple of papers appeared about that. Seems to be good progress. It's this. There's some intuitively clear that why it should be, but there's no simple theory or anything. It's probably time depending on the problem. It's not clear at all how to use this more advanced algorithm in that sense. And there have been attempts to do that. It's not convincing, and it doesn't seem to be working. Another interesting question is that what I said several times, right, is that it's not natural here that data process is independent from stage to stage. Very often it has some type of autocorrelation structure. But at least it's Markovian. For example, if we model the time series as a time series, it can be using Markovian structure. How to do that? In some cases, it's possible to do, but there's a cost of that. The state space increase, and there's still a lot not clear about that. Okay. Now, I'm not sure I should talk about that because, you know what? I'll come back to that if I'll have time, about risk averse, distribution robust, risk averse. It turns out that this type of this algorithm can be extended to distribution robust risk averse approach with almost no additional cost of that, surprisingly. But there are problems with that. I don't know. For that, I'll have to talk about all this theory. What is a distribution robust, risk averse? I don't think I will have enough time to that. It's possible to still write equations. I probably will come back to that if I will have time. Okay. I'll come back to that if I'll have time, okay? Now, one of the questions that was asked, what is really the value of solving multi-stage problems? This classical example that became now classical example is that we solve this problem with 120 stages. It was for period 10 years on monthly basis. It was a problem of this power generation. Maybe I'll have time to talk about that. Yeah. 120 stages is a lot. Should one really do that? Now, in many, when one tries to solve multi-stage problems of that, and usually it's not stationary. But very often it has sometimes periodical behavior. The problem has periodical behavior. Know this example that if I'll have time I will talk about that. This is how much rain or inflows, or what inflows will be per month. So there's historical data, and that's supposed to be more or less, at least stochastically, repeated every year. Right? So there's a period of 12 more or less, how this model usually, things like that. It's not stationary, but nevertheless, there's some type of behavior here, of this structure here. So now I probably will talk something much more familiar to you. And this seems to be another thing that works quite well. So I wrote a general risk functional, but you can think about that it is expected value. And what appears here, this is what is you probably all will know now, infinite horizon, and this is discount factor. I think about that as expected value. It's also possible to formulate for risk, but let's do this for expected value. And we solve again probably linear type of this. We have linear, all linear of that. Now, very often what happens that the this random process, data process has periodical behavior. This is how it's modeled of certain period, say 12 months. So in other words, it repeats this every 12 months, stochastically, it repeats itself. And then we can think about, we look at the infinite horizon with discount factor. This is not standard. Okay? If we do this like that, okay, then your value function, we still assume stage-wise independence here, but even then it's difficult to solve. Right? The value function of that are the same because we look, they repeat itself with period m. And then it's possible to write this Bellman, what is called Bellman operation, so Bellman equation or Bellman operator, which in this particular case will look like that. Now, again, you can think about that expected value. It's possible to write in general for risk functional. Maybe I'll have time to talk about that. Okay. So what happens if we do that? We reduce say 120 stages to 12. One of the problems when we look at this time horizon, why they needed so many stages? Because if we don't do that, there's what is called end of horizon effect. The algorithm at the end say, oh, use all your resources. It doesn't care what happens afterwards. Because that too, they use it, originally it was planning for 5 years, and then next 5 years was given just because of the final horizon effect, that it will not, algorithm will not suggest use everything now. Because after its time is stopping there. Now, when we do it like that, it's this equation of time, it's automatic because it repeats periodically. And it turns out that it's still possible to apply to that this SDDP method, this cutting type of method. Also, there's some questions about it, how to apply that. And it works quite well. First, again, for first stage, which is really, for first couple of stages, it gives more or less the same solution as solved in all these 120 stages. But it's computationally, it's reduced computational effort enormously. And it seems to be working now. Now, of course, this is a period m here. Right? One can take period m equal to 1. In other words, one just, then it will become the standard way this how people do that. I suppose this, it will be this classical Bellman equation, which people use here. This is not, I don't think this is something new here from this point of view. But what is new here that still the method turns to be working and working quite well, this cutting playing time methods. Okay, so one can also write this Bellman equation, and there's a Bellman operator. It's possible to write this, as you all know. Of course, it's because of the periodical behavior it's defined on the product of this type of them. This is how it looks in this particular case. And then by more or less standard methods, it's possible to show, right? This is a contraction mapping where this is discount factor. Where this is this subnorm of that, it's one take this all of them. Because of that, if one define an appropriate space, bounded functions, it has a unique fixed point, and this one can think about that in classical way. Now, there are several interesting questions about that. This is this is something, at least in this area what I talk, is something very recent. Surprisingly, it works. And there are various questions related to that. Okay. Suppose for the moment we have this period 1 for simplicity. We need to still, we have this, the corresponding process here, which repeats itself, but it has continuous distribution. We need to discretize that. Suppose by sampling. By using this discretization, we approximate the true cost to go function of that, which is a solution of the corresponding Bellman equation, by this sample approximation. It's not difficult to show that one has this type of inequality. This is subnorm. This I can, we know what are bounds, that uniform bounds of that. This is basically what I've shown you before. And then the coefficient here. What really interesting and strange, maybe even strange. What is the sample complexity of that? Even if we're period m equal to 1. You see this in applications that I'm talking about, that I'll show you in a moment. This discount factor is very close to 1. It's 0.99 something, okay? Very close to 1. So it's a very large number. What typically happens, so what is this for fixed gamma, for fixed discount factor, because we know what is the complexity of that, we have standard estimates of this sample complexity. But what is a very interesting question, which I don't know simple answer. What happens when it approaches 1? Now, what this bound suggests that relative error will grow like 1 divided by 1 minus gamma. Why? Because as gamma, as this discount factor starts to approach 1, right, the value of that grows also like 1 divided by 1 minus gamma. It's very easy to show using this, geometric series, sum of geometric series. Because of that, the theory more or less says, which the theory what we have says that relative error as function of the n of the sample size should be proportional to 1 divided by 1 minus gamma. What is interesting from, and this is, we still have very limited number of experiments, it works much better than that. Why? I'm not sure. So this is a question. So there's a number of questions here, this complexity of that. One of this specific question for this approach, what happens with sample complexity when this approach 1? And this is important for applications, at least applications that I will show you example. So it's one of the questions. Now about duals. This is, you asked me about the duals, it's exactly what I will talk now. If we look at this problem, this is linear problem. Right? Suppose we have finite number of possible realization of that. finite number of possible scenarios. In principle, I can write it as one linear program. This is, everything is fine. Theoretically, it will be huge, but it's a linear program. It has dual. Can I use the dual for calculations? What happens in, for example, in this approach, that a classical SDDP method, the cutting plane methods, give bounds. It gives the lower bound, which given by the law approximation, and it gives stochastic upper bound. Stochastic. One way to compute this lower bound is standard, but the upper bound is that eventually one solves this infinite horizon problem here. So I can cut it somewhere. I can take this, cut it to something. It's not difficult by geometric series to estimate what will be remainder of that. Right? And then I can approximate it. The problem is that when this is very close to 1, right, I need to take the corresponding very large number here to error, to remind the error to make it small, that I can disregard it or control it. So when this upper bound, this what we standard upper bound, what we had before, does not work when this discount factor is, say, 0.99. And this is a example that we had to deal. This is really, it's even sometimes even more, 999. Okay. Now, what is interesting, and it actually was known for quite a long time, but it was not applied. It's possible to look at a dual problem. Remember, it's a huge linear problem, right? One hopes to write dynamical equation for dual problem. And it's possible. Right? And it's possible to write it in a dynamical way. It's usual one write the Lagrangian, and then change, look at the saddle point, change min-max, and it will look like this, the dual. What is this? What is a little bit surprising here? Then one it look at the dual problem, and it's now this are Lagrange multipliers for dual problem. This is dual. One can write. They do not decompose into in a primal problem. When you solve that, it decomposes for every possible scenario, for every possible discretization or marginal distribution. Here they do not. What can I do? It is like that. Right? Nevertheless, one can do similar things. Assuming this independence, stage-wise independence, one can write dynamical equation. When you have discretization, it's like that, and one can solve that by using these cutting planes, similar to what we did for primal problem. One can compute the value function. It's take a little bit more time because it doesn't decompose depending on how large the problem is, but it's possible to do. And it works. Why? I don't know. It works even when the discount factor is very close to 1. I have a few minutes left. Okay, this is became famous example. Some of you probably saw it many times. All right, this when we started to work about 10 years ago about that. It was a Brazilian power system generation, and that was mainly from the electricity was mainly produced from water power. No, it's changing now from what I understand, but the example itself became classical. It was the system, this is the dams that they have, many of them. It's that time it was aggregated in 4 different regions. So the state space was 4-dimensional, and the uncertain was inflows every month. It was on higher level, it was a monthly basis, and that was originally was supposed to be playing for 10 years because we had a monthly basis. So it resulted in multi-stage problem of 120 stages. Now, how the influence of the water coming every month was modeled as a certain periodical autoregressive process on monthly basis based on historical data, and this model was built. And the decision was decision variable how much water used every month on high level, and it was disaggregated weekly, hourly, trading. It's complicated, but this is at least what the general. Okay, so it has periodical behavior because there were dry reasons and rainy reasons on monthly basis, and this is what we tried to solve in the beginning. What was first of all, the model was built certain type of model of autoregressive process periodical because it's monthly basis. Then it was discretized. The original distribution were continuous coming from time series model. We discretized it using 100 samples per stage, and it's stabilized around there, because one can compute upper and lower bound. And this is it was also used with the risk, trying to control the risk. Risk is that here that one doesn't want, it's on monthly basis. So risk is the cost of electricity for consumers should not go through the roof every month. And it depends how much water they can use, because using water almost free. So, otherwise, if there's not enough water, one has to use some very expensive type of gas and oil and so on. And these were solutions. And it turns out we also solved that using this periodical behavior, and it gave very similar solutions of that. It was natural, depending on a discount factor. So if one uses this discount factor, this is, imagine it's a period 12. So if you take in the power 12, it's almost 0. But if one, they really use this discount factor. Why? Because it gives 12% on yearly basis. So you see, it's very, very close to 1. So for that, our standard upper bound did not work, because one has to estimate the tail of infinite series too large. This numerically didn't work. So we tried to use that using this type of the dual bounds, and it works surprisingly well, even for that. Now, you see, it's still 4 state variables here. What happened is first order autoregressive process gave reasonably good approximation of the data. Because of that, one add this, because of this autoregressive structure, one add more 4 variables to state. So originally it was 8 state variables. Now I think they decided to go to 10 regions. It's not clear how to work and all that. There are many, many questions about that. This is probably the last thing that I showed. I think I'll have to finish now. This is example. This is how low bound works. For this, remember, this is periodical problem with 12 stages, which repeat itself. You cannot make discretization here of the state space for 12 periods. Right? This is low bound, which is monotonically increasing, and give low bound for the true value. For the value of the problem, this is for discretization. Now, in order to solve this upper bound, one solved the dual problem. You see the strange thing. What happened is that if one use the standard way, adding more and more cuts, at a certain point there are too many cuts. Many of them redundant. You don't know which. Okay, so because that converges quite slowly, when gamma of this discount factor was very close to 1. So the simple idea here to restart the procedure, say every 100 iterations for the dual problem. Because how it works, one look at this upper bound for each value function, which current upper, and then start to add cuts. So this works reasonably well, this type of procedure, by removing all the cuts and starting it from new. Because that's a little bit jump up, because you started anew, using the current upper bound, and that go on, and you can see that converge in a reasonable way when the classical one doesn't work at all. So it's still not clear. There are many questions about that. What is the complexity of that? What is the complexity of computation algorithm? What is the complexity of discretization, and so on and so on and so on. Now, I don't know. There's some other things I probably will not have the time about that. About stopping time, probably I'll have no time to talk about that. I will not have time to talk about this distributional robust. No, if somebody interested, we can discuss that. Yes, I think this. If I'll take this. Yes.
Okay, so we have one question from Rene Carmona. So he says, like in the finance industry, to get around with the curse of dimensionality, people usually try to estimate conditional expectations using some form of regression or even neural network fitting. So how would that approach be useful here?
It's a very interesting question. And let me tell you the story. Okay. I didn't have time to talk about this stopping time, which is, from what I understand, is the classical this methods that I talk about here based on convexity. Convexity is everything. Okay? So some problems are convex and some are not.
Sorry for interruption. I wasn't asking about stopping time. I was asking, Rene was asking about curse of dimensionality and the use of regression for estimating.
I'm coming to that.
Okay.
We looked at the method that you used in finance to solve that. I finished. And in principle, we can do the same. We're using cutting planes. And the method, and it worked reasonably well. I'm not sure that we didn't push it far, but it seems that we couldn't compete with the methods that you used in regression and that. Also, it works. We have examples. I can show you for this, for example, this particular. All right. I don't know. It's all open. But again, nobody solved curse of dimensionality. In my understanding, using the stopping time is what we use. It's the specific structure is very much used. Yeah. So, no, again, I heard all types of talks, and especially people say, "Oh, we solved the problem with 1,000 state variables, thousands, millions of state variables." I doubt. Let's put it this way. Or there's some very specific structure. Even so, no, we did experiments. We increased the state space twice, from 8 to 16, a little bit artificially in the problem that we solved. And if how it was constructed was highly correlated, the real dimension probably much smaller than 16. It worked. But the moment you separate that, the complexity jumped enormously. Who knows? So When it works, it probably works because the one doesn't need to approximate the value functions everywhere. Why? What specific case? We don't know. I don't know if this answers the question. Answer the question or not?
I think it's the use of functional approximation, especially neural network, is always, I would say, like tricky in terms of theoretical analysis. But also it's harder to compare because to make functional approximation work or to make regression work, one would definitely need additional assumptions. So I think this is, I personally think that this is really a very interesting, like open problem to think about.
It's different way of looking at it. Sometimes it works. We couldn't compete with this regression methods that at least these few experiments that they did, maybe this we didn't push it so far. But this is examples that, if I understand correctly, are very specific. Now, there are many possible approaches now. One approach to use parameterize, to make parameterization of possible policies. Sometimes it's reasonable. So there are still many open questions.
Yeah. And is it possible to parameterize the cutting planes?
I'm not sure what it means. Of course, they're parameterized. The cutting planes, it's defined by a finite number of parameters. Mm-hmm. It's a linear, depending on how many. People now use, very popular become to use these affine policies, especially in robust optimization. I didn't talk about it, but this modeling that is a random process is not the only one possible. Okay, sometimes it works, from what I understand, sometimes it doesn't. Nobody knows why, at least that's my impression.
Thank you. So we have one more question from the audience.
Yes.
So the question is, does it make sense to use quadratic approximation to get a lower bound rather than using a linear one? And let's suppose that we do have strong convexity or just some nice properties. Would it be better to use a better lower bound?
I don't know. Vincent tried to do this. I am not sure. I don't know. If I will see convincing way of doing that, I'll change my opinion. I don't know. This is using this cutting planes is classical, and it has very clear theory about it and clear understanding. It's very here we use only convexity of that. If using a quadratic approximation, one need to estimate the curvature of this, how strong and that, and it's very difficult. I'm not sure. I don't know. As I said, I don't have answers to all questions.
Yeah, I think just in classical optimization, if we do have strong convexity, then it makes sense to use quadratic lower bound, not cutting planes, but cutting planes with a quadratic penalties. And there are faster convergence results, but for classical optimization. So I don't know what has been tried in stochastic programming yet. Probably
I'm not sure what you're saying, because people use it as a penalization approach, trust region, correct? Not as lower approximation, not as approximation by cutting planes. I didn't see any quadratic type. I don't know, maybe I didn't see.
Yeah, I was talking about just classical optimization. We can solve classical optimization problem using dual cutting plane with an additional quadratic term.
Yes.
So when we have strong convexity.
So the quadratic term here is coming as a regularization term, correct?
We can think about it in that way.
Right? It is not that you try to approximate your function by quadratic functions. It's like quadratic function.
No, it's like we are. No, it's like we are instead of taking the supreme of a class of cutting planes, we're taking the supreme of a class of quadratic functions. So as a tighter approximation.
I don't know. I didn't see this even deterministic papers like that.
Oh, there is such a
There's
result.
okay, maybe. I don't know. I can say that there have been attempts to use penalization with this quadratic term, no, this trust region table. It's absolutely unclear if it works or not. I didn't see any convincing theory about that, and the numerical experiments are as good as this particular example. I don't know. In that case, it will be very difficult because your value function is complicated. You have no direct way of even knowing what is there. I don't know. It's difficult.
Mm. Yeah, so finally, like Rene Carmona made a remark that, so it seems like it's reasonable to use Monte Carlo scenarios because the random process, psi t, is not affected by the controls. So it's like optimal stopping in option pricing.
Yes.
So is there like a major difference? Like for example, like if the stochastic process is actually heavily influenced by our own controls, then it's harder to do Monte Carlo simulation. Is that the right way to think about it?
If the stochastic process itself affected by our decisions, everything that I said doesn't work. And one of the reasons is that it destroys convexity even in linear case. So all these methods that I said will not work at all. So this is a big difference. And that I can imagine that there are many applications that our decision affect the distributions. Clearly, how to deal with that, I don't know. But this what I said will not work.
Yeah, so I think there are like approaches, for example, by, for example, doing some sort of like Monte Carlo tree search. Like even if scenarios and actions influence the randomness, it's still possible to get good heuristic or approximation algorithms. But understanding convergence and approximation guarantee for those algorithms require much stronger assumptions, or sometimes there's little theory about those.
I agree. There are many open questions. I listed some.
All right, let's see if we have, okay, so, okay, just from Rene again. So Rene agrees with the comment that whenever the process is independent from the controls, this is a significantly simpler problem. And there's not much more we could do theoretically, provably, once everything is entangled together.
It's simpler, but it's still very difficult.
Of course.
This is what we have now. I don't claim that I have answered to all questions. No, certainly not.
Okay, it seems like we have all the questions answered so far. And so thank you, Alex. And we really enjoy it. So we'll stop from here and we'll regroup in 1 hour. And so I think there's like there are discussions in the chat and in the Discord and also in the Gather Town. So let's move this discussion like offline from the Zoom seminar.
If somebody interested, I'll be glad to talk. There's
Thank you, Alex.
many still open questions. Something no, something no.
All right. Thank you, Alex. Thank you all very much.
Okay.
Yeah, Chaba, do you want to add something?
Sorry?
No, I just want to thank again. Yeah.